title of my report is Integral Equations with the weak singularity and splines of the fifth order of approximation. The authors have previously shown that local splines of the second, fifth, and seventh order of approximations give good results for interpolating functions. In this paper, we will focus on the use of local splines of the fifth order approximation to solve Fredholm integral equations of the second kind with the weak singularity. Previously, the second order and seventh order approximation splines were used to solve integral equations with the weak singularity. A comparison of results for numerical solution of Fredholm equations of the second kind with this weak singularity by splines of the second, fifth, and seventh orders of approximations are presented. Let we have the integral equation. Here, the kernel of the integral equation has a weak singularity of the form. Let us recall how fifth order approximations are constructed. Let a grid of ordered nodes be constructed on the interval AB. Let Tj be the nodes of the set on the interval AB. So let we have the set of nodes on the interval AB and suppose that the system of functions forms a Chebyshev system. We define the basis splines on the interval xj plus 1 from interval AB, solving the system of equations. In the case of polynomial system, the fundamental system has the form. Let ui be the value of function u at the node ti. At the beginning of the interval AB, we apply the approximation with the right splines. Here we can see the plots of the right basis splines, the middle basis splines, and the right basis splines. And here we can see the theorem that gives us the errors of approximation, the function u on the interval tj plus 1 with the left, the right, and the middle basis splines. All these splines we apply for approximation on the finite interval AB, on the segment A. And here we can see some numerical results when we have some functions u. Let n be integer and AB real. Suppose that a grid of nodes with a step h is constructed on the interval AB. Let the set of nodes be equidistant set of nodes. Let us consider the numerical solution of the Fredholm equation of the second kind. The linear Fredholm equation of the second kind has the form. Here f is a given function, k is a kernel, and u is an unknown function that needs to be obtained. As already noted, the splines approximation of the function is applied separately to each grid interval. So we represent the integral in the form. And the function kernel multiplied unknown function can be approximated with the next expression. Kernel multiplied the approximation of the function u. So we have to obtain some coefficients Cj that such that they are the values of function u at the node Sj. Thus, we obtain the expression. And now we have to solve this system of equations. Here we can see some integrals that can be computed exactly. Otherwise, we can use the quadrature formulas. In this case, it is necessary to take into account the error of applied quadrature formulas. When solving integral equations, local polynomial splines give an acceptable solution with a small number of operations in a short time. If the integral has a weight function, then we can use the Gaussian types quadrature formulas. In this case, we separate the singularity into a weight function. Numerical examples. Example number 1. Consider the following integral equation, where q from t is chosen such that the exact solution is exponent of t. Figure 1 shows the graph of the right side of the equation. And we can see the solution of our integral equation when we use the polynomial splines of the fifth order approximation when the quantity of nodes is 10. So here we can see the error of approximation when we used the splines of the fifth order of approximation. This slide shows us the plot of the error of the solution obtained with the polynomial splines of the second order approximation when we used 50 nodes, and the plot of the errors when we used the polynomial splines of the fifth order approximation when we used 10 nodes. So we can see that the error of solution is just the same, but the quantity of nodes differs. Shows us the results of the solution with integral equation. The left plot shows us the errors of the solution obtained with the polynomial splines of the fifth order approximation when we used 32 nodes. The right plot shows us the errors of the solution that were obtained when we used polynomial splines of the second order approximation with 100 nodes. Here we can see how we can use the splines of the second order approximation. Here we can see the basic function, and here we can see the error approximation when we provide the interpolation functions using the splines of the second order approximation. The approximation we construct on every interval xj, xj plus 1. This slide shows us the result of solution the integral equations that is taken from this paper. To the left we can see the plot of the errors of the solution when we used polynomial splines of the second order approximation and 100 nodes. And to the right, we can see the plot of values of the solution when we use polynomial splines of the fifth order approximation with 50 nodes. If the integral has a weight function, then we can use the Gaussian types quadrature formulas. In this case, we separate the singularity into a weight function. As a result of solving the integral equations, we obtain the values for the solution at the grid nodes. Implying the same splines, the splines of the fifth order approximation, we can connect the solution values at the grid nodes with the line. And in addition, we can find and visualize the first or second derivative of the solution on a given interval. Thus, with the help of splines of the fifth order approximation, we are able to obtain a solution at any point in the interval as well as the derivatives of the solution. Thank you. Questions?